we're going to discuss Leetcode number 62, which is unique paths. So we're given an m by n grid, which means it's a two-dimensional grid, and we have a robot at the start and a star at the finish. And we have to find how many possible ways are there to get from start to finish. And the restriction is that the robot can only move either down or right. So he can go like 1, 2, 3, 4, 5, 6, 7, 8, 9, or he can go right, down. Like there's a lot of ways he can go to basically reach this uh, finish square by only going right and down. So we also have another restriction that m and n will be at most 100. So this is an important thing to note. So the approach I'm thinking of is basically just do a recursive loop. So basically you start here and then you just find how many you go right, and then find how many ways are there to get to the end from the right, and then go down and then just find how many ways are there to get to the end from down here. So and then you just recurse, and then if your current position is equal to the destination, then you return 1. So then it's going to backtrack and then calculate all the possible paths through recursion. So yeah, the idea is simple. We go right. So the number of paths for this square is the number of paths on the right for the right square plus the number of paths on the down square. So if there's like, let's say 10 paths to get from here to here, and there's 12 paths to get from here to here, then from here it will be 10 plus 12, right? So we basically just recurse like that, and then the base case of the recursion is when you're on this finish square, there's only one way, so it's just return 1. So let's do that. Now note that we always start from the top left and end at the bottom right. But then as we recurse, our start position changes. So then we need a recursive helper function, which will give us the unique paths from um, so this would be a start x coordinate, a start y. So we'll say that this is 0, 0, 0, and then here x is 1, x is 2, x is 3. And as we go down, y is 0 on this top row, y is 1, y is 2. So, and then we have end x and y. So we would call this function by saying unique paths, and then our start x is 0, our start y is 0, our end x would be the number of columns, right? So if this is x is 0, x is 1, x is 2, x3, so our end x would be the number of columns, right? And if you look at the example here, n is actually n is the rows, m is actually the number of columns, right? So we pass in m minus 1 since we're starting at 0. So our end x should be the number of columns minus 1. So in this case, 0, 1, 2, 3, 4, 5, 6. So our end x in this case would be 6, which is m minus 1. And then our end y would be n minus 1. So In this function, let's start with the base case. So basically, if start x is equal to end x and start y is equal to end y, then we return 1, because when you're already at the destination, there's one way to get to the destination. And then we make sure that our x and y don't go out of bounds. So like from here, if you try to go down, there are 0 ways that you can get to finish because that square doesn't exist. So we'll go like if start x is less than 0, or start x is greater than end x, or if start y is less than 0, or start y is greater than end y, then we return 0, because if you're out of the board, then there are 0 ways that you can get to that destination. Otherwise, we return unique paths of, so we try to go down. So going down is start x plus 1. Sorry, going to the right is start x plus 1. So this is going to the right when your y remains the same, but your x goes plus 1. So your end x and end y remain the same. So this is the number of ways to reach the destination, number of ways to reach end by going right. So if you go right, then it's basically unique paths of the right square, and then you add that with the number of ways to reach the end by going down, which would be start y plus 1. And then this would be the answer. But now, as you can notice that this is a little bit inefficient, because when you recurse from going right, you'll recurse, like when you recurse for going right, then in that call it will try to go right and down. So it will recurse for this whole down thing, and then it will backtrack and then try to go down, and then when you go down it will again recurse for this same square. So there will be a lot of duplicate recursions with the same square, um, because when you go down, you go right, you're back at the square. When you go right and down, you're back at the square. So in both cases, it will try to recompute the whole number of paths for this square, which means like it's gonna exponentially get worse recursing through each of the squares. So to fix that problem, what we're going to do is introduce memoization. So basically, when you've already seen the start x and the start y one time, then um, the number of ways to get from there to finish is the same. You don't need to recompute and re-recurse, right? So if there's like 50 ways to get from here to here, when it recurses for here, it's going to compute that 50, but when it recurses for the down square and arrives here, you can just store that somewhere and have it read it, so it doesn't have to recompute and re-recurse all the squares again. So we're going to introduce a memoization map to store the results that we've already computed. So if we run it to it again, then we can use the pre-calculated result. So I'm going to call it memoization, already known paths or something, and I'm gonna use integer because I want to know if that slot is empty or not, so I can use null to compare it. So and then I'm gonna make this a new integer. And the way I'm gonna think about this array is that the first this is the first one would represent which row, and the second one would represent which column, right? So for the first one, it's gonna be row 1, row 2, sorry, row 0, row 1, or row 2, right? So then 0, 1, 2, that would mean it's actually the n, right? It's the number of rows, which would be n. So this would be n, sorry, and the second one would be n, right? And then here we say like if it's not, so here we need to pass this in. So we say final copy this thing. Let me pass it here. And we also have to pass it in when we recurse. So yeah, where was I? Okay, so now here, if if the already known paths, so at so the first coordinate will be which row, right? So it would be the start y. If already known paths at start y and start x is null, that means we haven't yet computed it, then we'll store it in the memoized array. So instead of so this logic of actually computing the path would be placed over here. Uh, okay, so what we're saying is if it's not already known, right, because it's null, then we go ahead and compute it, right? Otherwise, if it's already there, or if we whether it's already there, otherwise if it's already there, then this thing will already contain a value, right? If it's null, then we go ahead and compute the value. So then after this statement, we're sure that this array will have the number of paths for this x and y coordinate. So we just return that. Um, so basically this computation would be only happening if we haven't already computed this before. Otherwise, we'll just look up from the previously computed value. So now if we run the code, we have some compilers. Okay, here, and x. Okay, so now our code compiled. Let's try to submit it. Cool, so it's pretty fast. Memory usage maybe can be made more efficient if you can find a way to only store the path as you run into the, so now we just have a predefined array, so it's just going to take up all the memory, and it's of integer type, not of the primitive integer. But if you can find a way to maybe use something like a efficient kind of set or something that you only store what you need, then that might be more efficient. But I think this is good enough, and yeah, thank you for watching.